Hi, good morning, everyone. Hey, thank you again for coming today. I'm Aviral, and I'm a professor of computer science at ASU, Arizona State University. And it's my pleasure to welcome our keynote speaker today, Professor Reinhard von Hanxleden. Okay, it's a bit complicated, but doable. Yeah, we all struggle. My name, yeah, I won't even start. Okay, so Professor Reinhardt completed his bachelor's in CS plus physics, my favorite combination. So that is my dream if I would have a chance to do that. Then he did his master's at Penn State and his PhD at Rice University with Professor Ken Kennedy. Then he started working in Daimler in Berlin and Airbus in Toulouse and Hamburg. And then this was last century. And then by the end of the century, he said, okay, enough is enough. I am going into academia. So then he joined Kiel University. Then he's a professor, full professor there. He's actually department chair there. He's been there for some time. And he collaborates a lot with Berkeley, Auckland, I'm assuming Partha, and some other people, and in ENS, right? This is in Paris. Yeah, ENS and INRIA. So he's a very well-known figure in this synchronous data flow computing, and so this all properties and timings of time-sensitive languages and application development. So, Professor Reinhardt.
Thanks, everyone. Yeah, that sounds good. Okay, thanks everyone for the kind introduction, and thanks for having me. So yeah, synchronous community. So somehow 12 years seems like a good time to reflect back on things. So some of you may know this paper by Benveniste et al. On synchronous languages 12 years later, which I think I have read at least 12 times. And so now let's see, on SCCharts, thanks for the opportunity to reflect on two things. Sequential constructiveness on the one hand, which is the semantics side, and I think that is what I will probably reflect on mostly about. And then also text-first modeling, that is more on the syntactic side, but something that I feel nonetheless is something that is characteristic for this language and which maybe has had even more uptake than the sequential constructiveness. Sequential constructiveness, that's more for, let's say, for the insight, for the semantics crowd. So that's for us, I would say. But text first, that is by no means specific to synchronous programming, but it's in general, I would say, for systems development. So reactive systems, to start at the beginning, they do some computation, they take some inputs, they produce some outputs, and in between they pause for a tiny moment. So that's the synchronous model of computation. Basically that the computation itself should take no time at all, and that all the time that is taken is just taken between the different reactions. So morally, this pause statement should really correspond to some physical time. Even if it's just a nanosecond, the pause statement should reflect physical time. And that is actually one thing that has not been quite true at the beginning, at the origins of synchronous programming, because there were some scheduling constraints because of the fixed point semantics. I will get into that in a moment later. That has led to the abuse of the pause statement to have it also inside the computation. And that's one of the things that we wanted to get rid of when we started with the sequentially constructive model of computation, that there is no need for these artificial pause statements within the computation, that they really are reserved for physical time. So that's part of the idea. So The origins of SCCharts, they go back on the one hand to Statecharts from David Harrell, and they also go back to a conversation that we had now about 12 years ago with National Instruments. So they are this all-visual company, so you may have known, you may know already their LabVIEW product, so everything is graphical, and they wanted to develop some language with a Statecharts-like syntax for hardware design. And they had heard good things about the synchronous paradigm. They wanted something with a solid semantics foundation, so they asked us, well, can you come up with a Statecharts-like language for hardware design? And we said, okay, well, let's have a look at that. And so Statecharts, that was the setting. We wanted to have some Statecharts-like syntax. And so here you see David Harrell's original citizen wristwatch that he used to explain the workings of Statecharts in his original paper. And here you see the foundations. On the one hand, you have these finite state machines. You have these automata here. You have them composed in parallel, so you have concurrency separated here by this dashed line. And you also have hierarchy, so you can have preemption. So in a nutshell, Statecharts are automata plus concurrency plus preemption. So that's what we wanted to preserve. And actually, David had this great idea, but he had some hard time to get it published. So he has a very nice account of getting one rejection after the other. And people thought, well, Statecharts is this visual thing, and we want something solid, and solid has to be text and so on. So it took a while to get the first Statechart paper out, but then he got it out, and then people thought, well, this is a great thing. And there are these Harrell Statecharts, but there are also other things that we can do with this Statechart language. And there was this big debate, well, what's the right language, what's the right semantics for it? And so then in 1994, there was actually Michael Mendler who thought, well, this is also disorganized, and let's give some order into the chaos. And so he came up with this paper that compared all the, at that point, 21 different variants of Statecharts that you had at this point. So each column corresponds to one Statechart dialect. And he compared it according to different criteria. So for example, whether they would be graphical, whether they would allow negated trigger events, whether they allow timeout events. So there were these different categories, and actually the list goes on much longer than that. So the whole table looks like this. So it gives you an idea that there's quite a bit of semantic variation of Statecharts. And then David saw that paper and said, well, this is all nice and well, but actually you got it all wrong. And my semantics is actually something different. And he came up with a 22nd column where he explained, well, what exactly is what are the different characteristics of his language. And that actually motivated him to really write up precisely what is the semantics of this Statechart dialect. So 1994, already 22 different variants, and we are not even talking about UML Statecharts or Stateflow as part of Simulink and all these others, and SCCharts, of course, are not on there. So the bottom line, many different variations, but the same idea. You always have automata, and you have concurrency, and you have preemption. So back then, there was also the synchronous community that started to come around with languages like Estera and Lustre and Signal. And Florence Maraninci also saw these Statecharts and came up with a synchronous Statechart dialect. So the idea of synchrony is basically that you have deterministic behavior. So that is something that the original Statecharts, for example, did not have. So you could easily specify Statecharts where it was not clear whether you would take transition A or transition B. And for example, in the original StateMate tool that came along with Statecharts, there during simulation you were asked, well, do you want to take transition A or do you want to take transition B? And if you synthesize code, well, it was up to the code generator to just generate something. And so in synchronous programming, the idea was from the beginning to have a deterministic semantics, and if there are any uncertainties, then it's up to the compiler to determine that there are any uncertainties and to reject the program if there are any uncertainties. So that's the big change that came around with the synchronous paradigm and with this first Argos language. And there was a further development of a synchronous Statechart dialect into SCCharts. So Charles-André came up with this language that was commercially then also known as safe state machines, when STL Technologies marketed that as a language. And here you already see the basic characteristics that you also find in SCCharts. So for example, you have this strong abortion, which is here indicated with this circle at the beginning, which at some point has turned red. So now you have a red circle to show a strong abortion. You have a weak abortion. So the basic difference is basically that you that you either allow the internal behavior to still execute, so to still execute a last wish, that is weak abortion, and in strong abortion you don't do that. And so that is again one of these things where we want to have a deterministic semantics, and where we do not want to have a race condition between, on the one hand, internal behavior, and on the other hand, the preemption. So the semantics clearly says which way to resolve that race condition. Either the inner behavior wins and still gets to execute, or the outer behavior wins, that you do the preemption first. And you also have a normal termination, so-called normal termination. That just means when the inside threads, they all have terminated, then you take this transition here. Okay, so that was the setting when we were asked from NI to come up with a good semantics for a hardware-oriented state chart language. And one of the limitations they wanted to circumvent is that the semantics, the classical synchronous semantics, is rather restrictive. So for example, if you look at this little example, you have an initial state here shown with this bold outline, and from this initial state you take a transition if some variable x, some boolean, is not true, just using the standard syntax here that we know from C, for example. And if we take this transition, then actually we set x to true as part of the process. So this is totally normal behavior. So the moral equivalent in a C program, for example, would say if not x, so if something is not done yet, then do something and then record it by setting x to true. So perfectly fine. There is no race condition here. There is no concurrency. Everything clean and dandy. However, it's not allowed in SCCharts or in STL or any of these other languages. Why is it not allowed? Well, we do not have a fixed point here. X is true and false within the same tick. So remember, in synchronous programming, the computations don't take any time, and here at the same time you would have x true and false at the same time. And if you come from hardware design, this is totally natural. A wire cannot be high and low at the same tick. But if you come from software design, this is a rather annoying restriction, because again, there is no race condition. And so that was the idea of sequential constructiveness, to really take this clear scheduling information that you have here. Of course, you first test the condition before you actually execute this then branch, to really take this information for scheduling to give a clear semantics. So we wanted to preserve the nice properties of synchronous programming, that we have deterministic behavior, that we want to have static checking, so no runtime surprises, and we wanted to have efficient synthesis. However, we wanted to reduce the pain. So just as I outlined it earlier, we want to make it easy to adapt, especially if you are socialized as a programmer and not as a hardware designer. And we want to reject only models where really determinism is compromised. And so the approach is to harness scheduling information from the sequential or imperative constructs. So that's the bottom line. So we thought back then, and that was actually, I think, at a meeting in Bamberg with Partha and Michael Mendler, that we came up with this basic idea. And we thought, well, this problem solved, easy enough, but actually it only started then. So it turns out to be not all that easy to really pinpoint it precisely, and we find it to still be a rich research topic. But so now the language, before I explain a little closer what the SC model of computation is about. So first of all, to get an overview. So here's the hello world of synchronous programming, the ABRO. So we have some interface declaration, we have some initialization, we have a super state, we have concurrent regions, we have initial states shown with this thick outline. We have final states shown with a double outline. We have a delayed transition and a trigger, so that is the non-immediate transition. The immediate transition, they are shown with a dashed line. So that means that as soon as you enter a state, you can possibly take this transition, whereas with a delayed transition, the solid transition, you always have to reside in a state for at least one tick. So that's the main difference. And then we have the stronger board, remember the circle now shown red, and we have the termination transition. So that's the graphical syntax. And now as to the semantics, again, the idea is that the sequential control flow overrides the normal requirement of write before read. So that's part of the fixed point idea, that when you want to read a value, any potential writers to that value have already executed in that tick. So that's why the general rule is write before read. For example, in SRL, you have to, if you emit a signal and you test the presence of a signal, you first have to emit the signal and then you test the presence of a signal. So the idea is that writes now are visible only to reads that are either sequentially downstream or that are concurrent. So that means that writes are not visible to something that is sequentially before. So that's why we could write in the then branch something that was read before. So that is the one important change that we do here. So that is one thing. And then we go a little further by wanting to allow two different writes. And here we pick up on a concept that is well established already in SRL, the concept of a combine operation. So the basic idea is that under some circumstances we want to allow concurrent writes. So usually we just want to allow one writer so that we have a unique value. But in some cases when these writes are confluent, then we want to allow them. And so here, for example, if we have some write command that says, well, increment x by 5, and the other write command that says increment x by 3, then these two writes are confluent. And that is something that has been well established already in the SRL language with this combine operation. So if we specify some output signal x of type integer, then we say, well, you can resolve that if you have concurrent writes with this addition operation. And then, of course, if you have two increment by 5 and increment by 3, then combined they will add 8 no matter in which way you schedule these. So the usual way that you specify that in SRL is to say that such a combine function has to be commutative and associative. We do it in a slightly different, slightly generalized way by saying, well, we have a combination function if we have a function that takes two operators, and if it does not make a difference in which way we add two other values y1 and y2, whether we first add y1 and then y2 or whether we do it the other way around. So that's the basic point of having confluent operations, that it doesn't matter if you schedule concurrent operations in which order you do so. And so, for example, addition is such a combination function, but subtraction is also a valid combination function, even though it's not commutative. So that's why we use the slightly different definition here. So if it's associative and commutative, then it is a combination function, but not necessarily the other way around. And associativity in itself is also not sufficient or also not necessary. So now we are armed with this concept of a combination function. And based on that, we can now define relative and absolute writes. So here again is the definition of the combination function. And we say that we have an update or relative write if we use such a combination function. And in this case also this E has to be an expression that does not reference X and whose evaluation does not have any side effects. So these are our relative writes. And everything else, all the other writes have to be absolute writes. And in our SCChart compiler, we assume that relative writes, that they have this form that we saw earlier, like plus equals or minus equals, that kind of thing. So all the others are initializations or absolute writes. So any write that is not relative. Okay, and based on that, now the sequentially constructive model of computation defines this IUR protocol. So we schedule variable accesses within a reaction. So if we have sequential accesses to a variable, that is unconstrained. But if we have concurrent accesses to X, then we must follow the protocol that says first we do the initialization. Then we can have an arbitrary number of confluent updates, so updates of the same type, so you cannot mix, for example, addition and multiplication, that kind of thing. And then an arbitrary number of reads. So in each tick, for each variable, for each set of concurrent accesses to a variable, we want to follow this schedule. That's the protocol that we have to follow. And I have the feeling that the mic is it still working? Yeah, okay, it's maybe a glitch there. Okay, so far so good. So now we can accept many more models, like the one that I showed at the very beginning. But the world, of course, is not perfect. So in this case, we still have to reject some models. And by the way, here you see now a textual variant and the graphical variant. So this is already a first example of this text-first modeling. More on that later. But the basic idea is that as a modeler, you write this text, and this on the right-hand side is then synthesized automatically. So here we have two regions, regions A and B. And in the first region, well, we set x to 0, and in the second region, we set x to 1. And, well, it's still not clear which value we get for x at the beginning, depending on which way we schedule these. So we still have here a so-called causality cycle, and the compiler rejects the program. And this is another view of the same model here, from the same text. We here have a different synthesis that makes this more explicit. It shows the data flow, that here we have two writers to the variable x. So this is the so-called induced data flow. So one of the things that I really like, that with just this one click, you can already get a kind of data flow diagram that tells you which way the data flow, rather than just having this hidden broadcast that you typically have in Statecharts. So here's another example. So here we say, well, if we don't have x, then we set y to true. And here, if we don't have y, then we set x to true. Well, of course, it depends on which way in which order you do things. What result you get, non-deterministic, and again, the compiler rejects it. And here you see another view of the internal workings. This, on the one hand, on the left hand, you see this compile chain. So each of these boxes is for one version of our little program, and we can click on these boxes, and then we see these different versions that we have. And here at the end, we have the version of the so-called SC graph, or SCG in short. And we will get into that in a moment. But the interesting thing here is that here you see this cyclic dependency of the data flow and of the control flow that tells you that actually here you have a causality cycle. So that's the information that you see as a modeler. Not only that there is a problem, but also it is indicating where the problem is. Okay, and a variation on the example. Here you see we don't test the negation of x, but just x itself and y. And in this case, one might argue, well, x and y are false originally anyway, and so we do not speculatively execute anything. We only execute it if the trigger is fulfilled. And here, if none of the triggers are fulfilled at the beginning, then we don't have any race condition here. But it still gets rejected because we have a static analysis. So we do not test whether we potentially might execute something, but here the compiler statically tests whether there is a possible data dependency, and therefore it rejects it. Okay, so now we defined the IUR protocol, and now the question is, well, when is an SCCharts sequentially constructive? Okay, and so we now defined it to be sequentially constructive if for all possible inputs there exist runs, executions, that obey this initialize, update, read protocol. So we also say that it's reactive. And furthermore, if all these runs lead to the same result. So they are deterministic. And now one unfortunate fact here is that we have such a second requirement. So to be honest, when we set out to come up with this definition. Michael and I, we sat down for days and weeks, and we really tried hard to come up with a definition where you really had just this constructive concept, this constructive nature, that if you have a run, then it provides you a unique result. But unfortunately, there are counterexamples where you can have different runs. They all obey this initialize, update, read protocol, but they still lead to different results. And so, in a way, this really is less constructive, we have to admit, than STRL's constructive semantics, because in STRL, if it's constructive, it really means that you have a proof that you can come up with one execution that obeys the constructive requirements. And here we don't have that, so that is a weakness. But I will come back to that. But so this is now in the current definition that is a problem. Or I think it's a problem, or let's not say it's a problem, it's not nice. In practice, however, we say, well, we already have this analysis done statically anyway, so we have this static criterion. So here we say that it's acyclic, sequentially constructive, and there we do not have to worry about this definition up here anyway. So there again we have a very clean conservative concept. So in practice, in reality, this is not an issue, but it's still deep inside, it's still nagging me. So that's why I'm mentioning it. Okay, but in practice, don't worry about it. It's a rather straightforward static criterion like you have in other synchronous compilers as well. Okay, so now let's look a little closer into the inner workings. So one thing that we wanted to have is we wanted to have a very small concept or a very small set of core constructs. Like in STRL, for example, I think part of the beauty of STRL is that you have this very small core language, and once you have clearly defined the semantics of this core language, then you have defined the whole rest of the language, and all the rest is just syntactic sugar. And we wanted to follow the same approach. And it turned out that actually just 5 elements are sufficient to capture everything that you need for SCCharts and for other sequentially constructive languages. So what are these 5 concepts? Well, we have regions with an initial state and a final state, or threads of control. We have triggers. So we either, if a condition C holds, we take the first transition, or if it doesn't hold, we take the second transition. And now remember, these are dashed lines, and the dashed lines were immediate transitions, which you could take immediately as soon as you entered something. So the same thing with the effect, that is an immediate transition that just does a certain assignment. We have superstates that bring concurrency into the game, and we have states. And this is where we actually don't have a dashed line, but a solid line. So that means in a state, you really have to reside for at least one tick. Okay, so these are the 5 building blocks of SCCharts. And we map them to lower level constructs, namely the sequentially constructive language, SCL, and the sequentially constructive graph, SCG. So remember, the SCG we saw already earlier when I showed the cyclic dependency, that was an SCG. And so these concepts map one-to-one. The region becomes such a thread with an entry and an exit node. The trigger becomes a conditional. The effect just becomes an assignment node like this. The superstate becomes concurrency with fork and join. And the state becomes a pause node or a delay node. So a delay is basically like a stop sign that is cut in half. And the first part of the stop sign is the surface, and the second part of the stop sign is the depth of the pause statement. So if that rings a bell because you are already in the synchronous world, then good for you. If it doesn't ring a bell, don't worry. It's just surface is the beginning, depth is the end of it. And actually years later, it got pointed out to me, well, here you actually have just put it the other way around. Now, where actually time passes, here you have a dashed, or well, pointed to be precise, and where time doesn't pass, there you have solid lines, which is just the opposite from here. And, well, what can I say? Yes, it's just the opposite. It just worked out that way. So in case you're wondering, yes, that's the way it is. So down here, solid lines are the default, and up here, dashed lines are the default. Okay, So just keep in mind here we have the pause node consisting of this cut in half stop sign, and the nice thing if you do it this way is that you can move the surface and depth nodes around arbitrarily. It doesn't have to be stick in one place, and we will see an example of that later. So now one example, the little ABO, if it gets transformed into SCG, we see it over here. And now maybe a little closer, we see here, for example, these initial assignments to O1 and O2 up here. Then the fork join, we have two concurrent threads which correspond to these two different regions. And here, for example, in this one region, we test for A, just like down there. If A is true, then we take this transition, then we execute this stuff. If not, then we pause. And here we see this cut in half stop sign put apart or torn apart, so where the surface is down here, the one part of the pause statement, and the depth is up here, the other part of the pause statement. And so this allows you to arrange this SCG, which is also done automatically, in such a way that the control flow within a tick is always going pretty much from top to bottom. And if you have control flow that always goes from top to bottom, that already gives you a good visual indication that things are all right, that you do not have any causality cycles. And so that's why we like this way, this presentation, that we always have this top to bottom, and that's why it's nice to be able to take these tick boundaries apart from the beginning and the end. Okay. By the way, this would be an excellent point to ask any questions, just in case you have any. So I'm happy to have it a bit interactive, so I have enough material to cover us, but I promise at 10 after 10 I shut up no matter how many questions you ask. Not everybody happy so far? Okay, all right. So this is what we looked at now. And now let's also look at the other direction, upstream, while we have the syntactic sugar that I mentioned. So we have the core SCCharts that map down to here, and on top of that we have the extended SCCharts. So here, for example, we have the different types of preemptions or abortions that all then through different model-to-model transformations get mapped down to these elementary constructs. So if we take stock so far, we have extended SCCharts, core SCCharts, normalized or core SCCharts that I discussed in a little more detail, and then we have the SCL and the SCG. So now we have a fun language, and of course we want to somehow compile this into software or hardware. And so in the original paper we presented two types of compilation. On the one hand, the data flow approach, which is morally quite close to the circuit semantics of SDRL, which is also why it's good for generating hardware. And we have the priority approach, which is more software-like. And both of these I'm going to briefly describe in the following. So this is the data flow approach that corresponds to the circuit semantics. And again, we have this one-to-one mapping of the different, of the 5 different constructs we have here. So on the one hand, we have data flow code, equations, and on the other hand, we have these circuits that this translates to. And the basic idea is that control flow is realized as guards that tells us whether a piece of the program is actually executing if the guard is true, or if it's not executing if the guard is false. So maybe to begin with the conditional. So we have the guard that tells us whether the conditional is executed at all. So all the incoming guards, they are all together here. And then we have a guard for the true branch, which is true if the condition is executed at all and if the condition holds. And we have the guard for the false branch, which is just the opposite of that. And it translates to this straightforward circuit here. The assignment, well, we do this assignment if the guard is true, and X gets either the value E, the new value, if the guard holds, or it gets the old value, X. And this already may ring a bell with you, X prime and X. Well, this is basically just static single assignment. We have two different incarnations of the same variable. And that is actually one, I think, good way, legit way to think about sequential constructiveness. It's basically doing SSA for you. That it allows you to just reuse the same variable, and the compiler splits it up into all these different incarnations that you would have with SSA. And that also manifests itself here in this circuit semantics. Then for concurrency, well, if you know the circuit semantics from SRL, then you might realize these done and empty flags and the synchronizer. Again, if you don't recognize it, don't worry, but yeah, let's not spend too much time on it. But the one last interesting thing, I think, is the pause statement, which basically corresponds to a register. Because the pause statement is where you actually have to remember something, where you have to remember where control flow stayed from one tick to the next. So that's the only statement that generates state registers for you. All the others are just combinational circuits. Okay, so much for the data flow approach. And that is a quite robust approach. However, the only disadvantage of that is that because hardware, you cannot reuse the same hardware multiple times within the same tick. That's why it basically macro expands everything. If you reuse something many times, that leads to rather large code. So I will come back to that in a moment. But now let's switch to the priority-based compilation. Remember the second column, the more software-like approach. So here we don't simulate the control flow with guards and for basic blocks, but again with program counters and threads. So we do a thread dispatching based on priorities. So if you have data dependencies, if you have a concurrent writer and a concurrent reader, the concurrent writer must get the higher priority than the concurrent reader. So the idea is that in each tick you always execute the highest active thread and then the next highest priority active thread and so on until you have executed all the active threads. And that leads to a slight extension of the SCL language, namely SCLP, which is SCL plus priorities, or more precisely prio IDs, which fold the priority of a thread and a thread ID into one so that we get unique prio IDs. Because multiple threads can have the same priority, and to keep them apart, we add a thread ID to that. So in C, we implemented that as macros using computed gotos. I will get to that. So for me, that is one of the nicest things of code generation, these C macros. And maybe it's just because I'm a C nerd, but well, maybe some of you will appreciate it too when you see it. In Java, unfortunately, no macros, no gotos, so the Java code gets a lot uglier than the C code. The C code, I think, is really rather elegant. So here for the example that we saw earlier, we annotate this SCG with priorities based on data dependencies. So here, for example, we have a writer to be before a reader to be, and so that's why if you can read it, don't worry, I can't read it either, but trust me, this has a higher priority than this here. And we have this prio ID, which then gives unique prio IDs, so at runtime you can keep things apart. And now, the macros. Okay, so maybe first on the top right here, we have an SCChart that actually indicates the different execution states of a thread. So each thread can be either disabled, or if we fork off the thread, it becomes enabled. And an enabled thread is either actively executing, or when it's pausing, it's inactive. And then at the next tick, it becomes active again. So the bottom line is that for each thread, you have to keep track of two things, whether it's enabled or not, and whether it's active or not. And now let's have a look, a somewhat superficial look. So in class, I really like to spend at least half an hour on this alone, but now just a couple of minutes should do. So first we get a Boolean type. Then we have something, one of the nice things that a preprocessor can do for you. It can generate automatically a label that you can go to based on the current line number in the source code. So each line in the source code can give you a label, and this is some helper stuff. We will see this in action in a moment. And then down here we just have a little bit vector manipulation stuff to keep track of these two things, whether the thread is enabled or not, and whether it's active or not. So let's not worry about that too much. Then as I said, in the priority-based approach, we keep track of program counters. And now, of course, as a programmer, it's a little difficult to access the program counter. Usually in C or Java, if you just ask for the program counter, well, it's an address and I don't get that. But we can still do so at a somewhat higher level. And so that's what this set program counter macro does. It's so we have an array of program counters, one for each prior ID. And here we set a program counter to the address of a label. Remember, we automatically generate labels, and GCC allows you to take the address of a label. So that really translates to a program address, so something that a program counter will actually go through when you execute a program. And then we have a pause statement. So you may wonder, a pause statement in C, how can you do that? Well, here it is. Well, the pause statement, it calls this little helper function, and this helper function, well, it sets the program counter to a label, and that is this automatically generated label, which is just after the pause statement. So it basically says, well, here at this point, you don't execute any further because you go to this something, but next time when you start the tick, then you start right here, right after the pause statement. You start right at that label, and that's the pause statement. Then we have fork and join, which basically starts a new thread, but let's not get into the details of that. The parallel statement basically just says, well, the thread that reaches the parallel statement is finished now, go somewhere else. And here is a macro that allows you to change the priority. So let's not look into the macro, but the thing is that the thread can change priority within the tick, and that allows you to do back and forth scheduling. If you have complicated dependencies within a tick, then you can resolve these by allowing a thread to assume multiple different priorities within the same tick. Okay, so now, what does a program look like for this SCG? Well, it looks like this, using the different macros that we have. So here at the beginning of the tick, so this is the whole tick function, we have some tick start macro. Let's not worry about that for a moment. Then we do these assignments. Then we fork off the same thread, the first thread. So this is the first thread. Then we have parallel to the second thread. We join it, and then some assignments again, and then that's the end of the tick function. And in between, for example, we have these pause statements. So what we see on the right-hand side is a C program. It may not look like a C program, but it is a C program just using these macros that we defined earlier. So we just can use GCC and compile this thing, and it does the right thing, a concurrent C program. And now let's look a little bit into how these macros expand. So here we have the first half that we saw in its expanded version. So here, for example, if we look at the pause statement at line 94, that translates to the program counter of the current thread ID, CID, gets the address of this label, and then we finish the current tick by go to this thing, and here we have the label. So that means the next time we start the tick, then control starts right here at this label. That's it. And let's look at the second half. So the one last juicy bit that I want to share with you is here at the end, because remember, the execution works this way that always we execute the thread that is the highest active thread. So from all the active threads, we take the one with the highest prior ID, and we want to dispatch that. And we store the information of the active threads in these bit vectors. So the task is that from a bit vector of active threads, you have to find the leftmost one, basically. You have to find the highest prior ID. And now, of course, it's a straightforward exercise to write a little C loop that does that thing for you. But still, it's a loop, and you have to go through the whole thing and many iterations and so on. But if you're lucky and you're using GCC and you're using an x86 architecture, there is this one assembler instruction namely bit scan reverse, that does just that. It takes an integer, 32 or 64 bit, finds the index of the highest one and returns that. And now with this one assembler instruction, you know which thread to execute. And there you now look into this array of program counters, and you use this index, the current thread ID, to just jump there. So it's basically two assembler instructions. The one bit scan reverse, and the other one is this computed goto that does the dispatching. And so I challenge you to find a faster dispatcher than that. So I think this is really rather efficient, and I just love it. Okay, so take-home message, in case you haven't noticed. You can do wonderful things with the C preprocessor, we can do wonderful things with computed gotos, and we can do wonderful things with embedded assembler. So I'm not sure how often we still teach these things, but I think you should really know about it, and it's really cute. So, classroom tested. So here, for example, there's a big model railway that we use, and where we also tell the students to eat our dog food and use SCCharts, and so a controller, rather complex controller. So originally it has 10,000 SCChart nodes, so that's before expansion, before normalization, and so it turns out to be pretty big. So remember, I said that's one disadvantage of this netlist-based approach. It gets pretty big. That's why we also have this other approach. So compile time, 2 minutes, not the greatest, but it's still okay, I think, considering that you have 650,000 lines of code. And the reaction time is pretty good, 2 milliseconds. So huge code, but it's fast, and it works. So much for the sequentially constructive basics, and it's also used in other languages. So for example, the Blech language, which I think is quite nice from the folks at Blech, and there are also other languages, but often they don't call it that way, which I think is fine because it's just a very natural way of programming. I think the sequential constructiveness. You do it all the time, it's just not so common in the synchronous world. Okay, so on that, a small number of core constructs are sufficient to really build everything that you need for reactive control flow. And on top of that, you can have, of course, lots of syntactic sugar. So the nice thing is that we can keep the core semantics clean and simple, and we can easily adapt it to different syntheses. But the resulting code is difficult to map to the original model. So SCCharts, they are also used now in industry for describing railway interlocking systems, and they have fairly harsh requirements on the validation of the code, and part of that is that the generated code must map back to the original model. And that has actually motivated a different approach, which we call the interpreter approach, which basically tries to generate code which is quite close to the original SCChart, and then gets compiled just using your usual Java or C compiler. So there, in a way, we call it interpreter because it's so close to the original model of the generated code, and that is something that is used now, but I would still like to work on it a little further. So this is something that I would say is still an active project. Okay. So much for sequential constructiveness and the beauty of that. And now let's, as I promised, go a little bit into the text first side. So SCCharts have been textual and graphical from the beginning, and in the Kiel tool that we use for our ecosystem, that the modeler writes textually here, and then the different graphical views are synthesized automatically. And that it's automatically done also has the advantage that you can do different views. You can also have more abstract views or more concrete views without having to redo it yourself because it's all done automatically. And we use this automatic layout from the Eclipse layout kernel, or ELK. And now taking a step back, so why are we doing this? Well, we call it pragmatics-aware modeling. So somehow that term doesn't seem to be all that popular, but I haven't found a better term yet. So it's basically borrowed from linguistics, where the field of semiotics is divided into syntax, semantics, and pragmatics. So pragmatics basically telling you in which way you should use different language constructs. And so here we basically want to use textual syntax and graphical syntax as effectively as possible. So the idea is that we want to free the user of tedious mechanical work, such as manually placing objects or manually navigating in complex code. And so I don't know about you, but sometimes something that I hear time and again, people saying, well, graphical, all nice and well, but I prefer to type. It's just faster. And I think many people feel that way. And if you're using a traditional, what you see is what you get, graphical editor, then I don't blame you for that. And so we really hope to get also you, if you prefer textual, to think about maybe to generate graphics along the way. You can still type, all nice, but generate graphics along the way. So the idea of pragmatics is that we want to explore new interaction methodologies, new analysis, and new ways to synthesize models. And the experimental platform I already mentioned, Kieler. So Kiel Integrated Environment for Layout. That was the Kiel tool, and at some point we moved on to Eclipse, and so we tagged on an Eclipse-rich client. So that's why now we have Kieler in that, and the Eclipse layout kernel. But the Eclipse layout kernel is basically just a Java library, so you don't have to use it in Eclipse. So, for example, the Ptolemy tool also uses Elk, even though Ptolemy is not running on Eclipse, but it's in Java, and so that's why it's also using Elk. And the key idea here is that we want to use the model view controller paradigm, which is probably familiar to you already from software engineering, used in a different way. But if we go back to scripture, what Trygve wrote back then, well, a model represents knowledge, could be a single object, or it could be some structure of objects. A view is a visual representation of the model, would ordinarily highlight certain attributes of the model and suppress others. It's just acting as a presentation filter, so different views. And a controller, that is the link between the user and the system, and it provides the user with input by arranging for relevant views to present themselves in appropriate places on the screen. So I don't know whether Trygve thought of automatic layout when he wrote that, but I'm certainly thinking of automatic layout when I'm reading that, because that's exactly what we want to do. That we want to automatically arrange different things on the screen to reflect your model. And so that's why this distinction between the model and the view works very well for us. And you can think of the model as the textual description, even though, of course, the textual description is also nothing else than a view. But if you write a model, then you write it in text, and the view is generated automatically for you by the controller, the automatic layout that brings it all together. And so actually sequential constructiveness, yeah, nice and well, and some languages are using it, and I think it works great and so on, but it's rather a niche thing, to be honest, I think, like maybe, but pragmatics, that really seems to be something that people find useful in many different ways. So this, for example, is a nice email I got from somebody, Bosch Siemens Hausgeräte, so they are doing dishwashers and so on. So they also use textual modeling for productivity, but they also want to have graphical views, and that's why they use our infrastructure. And just yesterday I looked at some statistics for Elk.js, which is the JavaScript version, the transpiled version automatically from Java. And well, about 2,100 stars. And for me, that is a very meaningful metric. That means 2,100 people, they downloaded our stuff, and they took the effort to click on it and say, I liked it. So I think that is really, for me at least, as interesting as citation counts. Citation counts are, of course, also interesting, but I think this is really a very nice feedback for the whole team here. And well, there are quite a few repositories depending on it, which is also, I guess, on the one hand flattering, but on the other hand thinking that maybe there's just 2 or 3, or at the best of times 4 graduate students maintaining all this, and there are all these many repositories depending on it. Slightly scary thought. Usually we don't hear too much from it, but if our server is down for more than 12 hours, then emails keep coming in, and the and the forum is filling up and so on. So people are really paying attention to this. So another language that also is following this text-first approach, for example, is lingua franca, which we are very happy to be part of. So it's really a great team that Adley put together there. And so they have also been following that. Here we see a little example of a text and a graphics synthesized from that. So yeah, text first. If you are coming up with a new language, a new way of doing things, then I recommend that you may have a look at this text first. So a couple of minutes outlook. Model order. So think of this as C-chart. So we have two states, state 1 and state 2, and we transition from state 1 to state 2, and we transition from state 2 to state 1. And now take a moment and in your mind play automatic layout and think of how you would arrange this automatically on a screen. Everybody has an automaton? Okay. All right, so this is a view. So here you see the two states with the transitions between the two of them. So, and it's perfect from the graph drawing perspective. There are no edge crossings, it's all evenly spaced and so on. So who of you had this view now in your mind? Don't be shy. Okay, a couple. All right, thank you. So now I have another view. So you may try to spot the difference and then think, who of you had that view in your mind? Well, here it's a bit of a wash, but but I would argue that the right-hand side, well, it depends, of course, in your natural language, whether you write from left to right or whether you write from right to left. But at least here, in my mind, actually, this is the more natural thing. So because it more naturally, it's closer to the mental map that you have here. I mean, it's also, of course, the names, first one, then two, but first you have this thing and then the other thing. But from the graph drawing perspective, this is just as good as this. Any idea why this is just as good as this from a graph drawing perspective? So somebody remembers how a graph is defined? Well, a graph is a pair consisting of a set of vertices and a set of edges. And, well, sets don't have any order. And this is, I think, where the graph drawing community has gotten it really wrong, or the graph community as such, because a graph, I would argue, in the real world, often a graph has order. And so we argue to really replace set by list. And that is what we also refer to as model order. So the basic idea is that you have a mental map that you then preserve this mental map. And that's what the model order does. So take-home message, automatic layout is practical. Users have not to spend precious time on manual layout, and they want to have control over how a diagram looks. And users typically do not love to surprise themselves or to have unstable layouts. And they also want to learn too much about different layout options and so on. Things should just work. And I would say that you should really revise the definition of a graph. And last minute now on sequential constructiveness, I told you, well, there was this nagging thing about not having deterministic results. And here, for example, that this model gets rejected. Well, why not let the order, in this case of regions, also again prescribe the schedule to resolve the race condition by saying, well, first we have the one region, A, and then we schedule region B. And this is already used in many places. So, for example, also in the Prezi language, that is also just doing it that way. So, in the synchronous world, this is anathema, but well, it may not be the first thing that we do that is a bit anathemic, if that is an adjective. And so it's still deterministic, still under programmer control. No more nasty causality issues, simpler semantics. I think it could become a lot simpler. Price to pay, well, no back and forth scheduling within the tick, but, well, I'm not sure whether it's really a big price to pay in practice or not. So, wrap up, we have 5 core constructs. We have this model of computation where we relax synchrony. We explore text-first modeling, and still plenty of things to do. And last slide, sequential constructiveness is natural for programmers and proven in practice. So far, it's a bit tricky to formalize precisely, but maybe with this last thing, it could become a lot easier. Should be taking even more advantage of textual order, and it's easy, and so to easily control the scheduling, that is the key. And on text-first modeling, well, it's natural for programmers and proven in practice. It harnesses the power of automatic layout, and we should take even more advantage of the textual order. Remember the model that I mentioned at the end. And easy control of the layout is key. So with that, thanks a lot for your attention. If we want to, we could still have a brief demo, but I could also show it to you later if you're interested in that. Okay, so thank you very much.
Time for questions, or maybe we can watch the demo.
Okay. Thank you very much for the nice talk. I had a question about slide 38, roughly.
Slide 38.
This is not the slide, maybe close to that. Maybe there's an overlay or so. It was where you introduced basically the dashed cycles. Maybe 43 is another line where that I remembered. Yeah, this one is good.
Yeah.
So you have basically you connect the surface and the depth. And I presume you want to have a cycle-free graph normally. This is an exception to that.
Well, okay, yeah, this cycle, that doesn't matter because that is at the boundary of a tick. So we don't want any cycles within a tick.
Mm-hmm.
That's the thing.
So it's basically sending information to the next generation or the next instance of this.
Right.
Basically
and
to the
so
future.
That information, right. And so, so this, remember this corresponds to a pause statement that maps to a register. And this register is where we remember a state from one tick to the next.
Mm-hmm. Okay, thank you.
Yeah. Okay, thanks.
Hi, thanks for the talk. There are obvious parallels to be made with what the real-time community has done. Do you have experience working with the real-time community, for example, for this idea of recurrent real-time tasks, periodic ones, or in real-time operating system deployments?
Yeah, so in a way, I think we consider ourselves to be part of the real-time community. And so, yes, you can think of this also as a cyclic executive, where you basically have this idea. So I would say the synchronous community takes it, is a bit more specific in that, or special, whatever way you want to call it, in that we have the underlying assumption that within a tick we do not pass any time, so that we have instantaneous computations, and that's why we typically have this fixed point semantics, which is usually not necessarily the case in real-time programming. Yeah, but it is, so this is meant for real-time systems, so like these railway interlocking systems that I mentioned, so that's a typical real-time application. Yeah, that's a
Thanks.
good point.
I mean, in other aspects, the context of this is more about correctness, and the real time is more about schedulability and performance. Oh, any other questions? Time for demo?
Okay, little demo, all right. So let's have fun. So demos are always exciting, so everything can happen during a demo, so let's see. All right, so I just got briefed from my students on this, so, because unfortunately I don't get to do this that often anymore. So. Okay, so I think the one thing that demos are really different from slides if you want to explore the pragmatics. So if you want to see how things, how you can interact. as a modeler. So here, for example, we have a little motor description. And so remember, if view can be very abstract, it can highlight certain attributes. So at this point, we start with a very abstract view that just tells you, well, we have 3 concurrent regions here, one that sets the speeds, one that controls the motor, and one that simulates time. And now we can look inside. And here, for example, then the simulation time, here we see, well, there's one during action that does the different things. And when I click through the diagram here, it automatically navigates the text to the portion that I'm looking at. So here, for example, we have this initial state, sim time state, during which we have this during action. And here we have the during action. And I can also go to a different, I can expand this, for example, the control motor. And if I click on a state, then it moves to the state on the left-hand side where I see all the details. So here, for example, these transitions here are very abstract. I only see the different priorities. But if I want to see more details of that, then here, for example, and the layout, the label management, this is now a very abstract version where I just show the priorities. If I want to show the full labels, then I click on original labels. And then I see that the diagram becomes a lot larger. And that's why it's a good idea to abstract things. But I can do these labels also in a bit more compact. So we call this semantic soft wrapping. And so now things are a bit more compressed again. And now let me do it the more abstract thing again. So just the priorities. So I can play also with the way the layout is done. So here it's done from left to right. And now let's do it, for example, all vertical. So this is a different layout that I get here. So usually the nicest thing is if we alternate between horizontal and vertical, if you go down the nesting option. So this is the horizontal and vertical thing. And now let's explore the set speeds. And so here, for example, we can play a little with the model order. So let's see. There was one pragma. So here, for example, if I want to add a transition from the acceleration state to the check-min state, I prepared something. So here I have this transition which is commented out. And now I'm going to uncomment the comment. And now watch what's happening to the... So here we have accel and decel and nothing in between. And now I'm going to uncomment it. And now, well, we have this new transition, but what we also notice is that the accel moved down, the accelerate, and the deceleration is up. Remember, before it was different. If I comment it again, so it moved around, so it's not stable. That's bad, even though from the graphical perspective, it's all equally good. And so now, the new thing is that we want to consider model order. So here I have this layout directive here, which actually forced it to not do the model order here. This layout directive, consider model order strategy, none. And now if I go to the default behavior, then we consider the model order that first we have state accel and decel, and now it stays that way, no matter whether I have the added transition or not. So I have better stability now. Okay, so that maybe gives you a little idea of what the interaction with this diagram looks like. Okay. All right, thank you.
That was awesome. Thank you, Professor Hanxleden. And with this, we close this keynote session. And the next session starts in 20 minutes at 10:30. So please come back in 20 minutes. Thank you.
Okay. Thank you again.